Where can I deploy it? How does it work? And when should I do it? So yeah, a little contrived, but I apologize. So first, a word from our sponsor, Apache Ignite, the best kept secret in Apache. All right, so this is speaking to a mostly TimesTen crowd. This is going to be kind of amusing, but applications talk to databases. Traditionally, in most cases, where does Apache Ignite fit? It fits in between the application and the system of record, or in this case, a database. What are the attributes about Apache Ignite? First off, it's 100% in memory. It is a memory-first application. It's a Java application, so it does have a JVM associated with it. Most of the storage is off heap. Actually, by default, in the latest version, it is 100% off heap, and you can choose to store other places in memory or on heap. It is a key value store or a file system. So 99.9% of our applications use the key value store, and the other 0.1% is the file system, which is Ignite file system, which is HDFS compliant. So it is an in-memory file system compliant with Hadoop. Always available. So this is one of the topics that we are going to be spending a lot of time on today. But Apache Ignite in itself, and I'm sorry, I'm probably wandering around inappropriately. So one of the attributes of Apache Ignite is that it is a distributed system. It is a peerless, peer-to-peer architecture. There's no master or slaves, and it is completely available within a single data center. So the open source project, Apache Ignite, is 100% available within a single data center, using the concept of primary nodes and backup nodes. So when you create a cache, you determine how many nodes you want as a backup and which one's your primary, and it's self-healing. So if you do lose your primary node, it will automatically elect a backup as a primary and create a new backup node. We can go into a lot more detail about that if you'd like, but this is just sort of giving you an idea of what Apache Ignite is before we go into multi-data center replication. It's scalable. So the way that Apache Ignite was built, I want to say that it was a happy accident that it ended up being quite a bit like the current NoSQL solutions out there in terms of how it worked with distributed systems. So if you're familiar with Hazelcast or Gigaspaces, it's a very different architecture as far as how it took a single database and distributed it amongst multiple nodes or data system. So Apache Ignite is actually very similar to Cassandra if you're familiar with Cassandra's architecture. And as you need more capacity, you can add another node to the system. It's elastic that way. It's also vertically scalable. So we talked earlier about how you can store data off heap as well as on heap. So you can take advantage of all the memory on your node if appropriate for your workload and your service levels agreements. So far, so good. I'm getting some nods, some people. Yeah?
So you have the mic recording the memory to the disk?
So, great question. So there's a couple of different ways, memory-only solution. So your persistence layer was your database. So you could plug in an Oracle database, anything that had an ODBC or JDBC driver. We'll talk about Cassandra and Hadoop in a little bit, but you had some type of persistent store because, well, we all know why. The latest release of Apache Ignite actually has its own persistent store. It is still memory first, so the data will always be written and read from memory, but will be a backing persistent store that is actually just memory page snapshots to disk. So it's pluggable. You can choose a persistent store. You can run without a persistent store because Apache Ignite is actually also a compute grid. So you can have, we've been talking mostly about caching and data grids here, but you can also have a compute grid where you can distribute computations amongst your cluster.
So my question is that the in-memory copy is a cache of the persistent copy in the disk?
Yep.
Okay.
Yep.
Can the memory and the disk be inconsistent in this one?
It's designed not to be. If there is, it's a bug. You're supposed to. If you have if you're using the pluggable store, the persistent store, you can either write behind. So you'd probably do a write behind, which would make it inconsistent for however long you choose it to be inconsistent for. So it could be fully ACID, which is my next slide. So it could be completely 100% ACID consistent, or if you would prefer a more eventually consistent system in terms of speed, the consistency could be off for however long it takes to persist that piece of data.
So if it's consistent, then the latency is the latency of the disk.
Latency of the disk, yes. Ignite was built about 10 years ago, before all this NoSQL hoopla was out there. So it is fully SQL 99 compliant, unlike things like Cassandra or Hadoop or Mongo, cache-based, Redis, et cetera, So you can write full SQLs, you can do joins, you can do group bys, you can do aggregations. Anything you can do in SQL, you can do against Apache Ignite. There is 2 types of APIs. So an API that is direct to the system itself, and we have Java, .NET, C++, pretty much any language that you're interested in, but also a SQL API. So you can write your application to communicate to the Apache Ignite using SQL. So what this puts on top of, for the reason I'm at GridGain is one of the issues with Apache Cassandra is that there is no SQL access. You have to data model specifically for your queries, and if you try to write a query that's not, your data model's not designed for, you're going to be in a whole world of trouble. Also, Cassandra is not an in-memory application, so I was with telecom customers trying to fight for microseconds and not getting them. So that on top of, I kept on hearing from Gartner, Gartner would come to DataStax, we pay them for the honor, and Gartner would say, you guys really need an in-memory solution. In-memory is the way things are going. Memory is the new disk. Gartner's on record for saying a whole bunch of that type of stuff. And DataStax wasn't listening. But my customers were. What?
So you're saying this replaces SQL 99 on the key value based data store?
Yes, we do. We use an H2 compiler to translate between the two.
Is that efficient?
It seems to be.
Okay.
The difference, we've seen about a 1% difference between direct API calls and SQL calls.
Well, you talk about the distributed system here, right? So you have a key value store. So.
That's the
Okay. Okay.
What?
Hive.
It's okay. Odd, but it's not that I've never heard these things before.
Yeah, I can imagine if you are doing a join, right, in a distributed system and your key value store, I don't think that's very efficient.
Well, yes. I mean, you can also, decide to walk up a mountain with 2 broken legs. You can also, relational databases, they let you do this thing called a cross join. And I'm not exactly sure why they let you do cross joins. Isn't that slow? It's the same type of idea, right? I mean, your mileage may vary. Whether or not if you write, what is the first rule of tuning a distributed system? Don't distribute the data. And luckily we have that option, right? So you can actually replicate your data on every single one of your nodes. You don't have to distribute it, which is great for lookup tables or dimension tables. So you don't actually have to replicate the data. We do allow you to shoot yourself in the foot.
So you also support the global index?
We do, yeah.
Okay,
and we also allow you to shoot yourself in the foot, just like relational databases allow you to do cross joins. We'll allow you to join 2 caches that are distributed that aren't share the same key. Just sit there and wait, because it's going to take a while, right? Way back, I was doing tech support for Redbrick. Redbrick was the first database written for data warehousing, so lots of star schemas. And somebody told me, hey, my query is using 3-dimension tables and a fact table. It's just taking forever. I can't figure it out. And this customer did not have email at the time. This just dates me a little bit. So they faxed me over the explain plan. And at the end of the explain plan, I'm like, so, you need indexes? It helps with joins. So, same thing. Really, really fast database. Not great if you don't use a layer on top of Cassandra, which is pretty cool because Cassandra does lots of good things, but it doesn't do SQL. And I've stood in front of people just like you for many years trying to get people to data model correctly. Still don't listen. They just don't listen. All right, so no rip and replace. So this idea that this will go in between your application and your system of record. I think marketing made me put that on the slide. But the idea here is that you don't necessarily have to create a new system. So things like Cassandra, Mongo, Redis require you to create a new application, right? You have to data model, you have to write your application to talk to that new database. You can accelerate existing databases if you're willing to rewrite your application to change the API calls to talk to Ignite versus talking to the underlying system. So you do have two modes that you can go through to deploy Apache Ignite. You can accelerate old systems, and again, apologies for the Oracle-centric stuff, but I'm getting a lot of people talking about Exadata right now. People are looking to accelerate Exadata in a lot of ways because they may be just strapped for cash, right? They can't afford to upgrade. So that's an example of accelerating existing applications. Or you can do Greenfield, which is probably what most of our clients do. We do also have a Hadoop Accelerator, so this will, HDFS can act as the persistent store, and you can either expose the Hadoop data in the Ignite file system, so it looks just like HDFS, but it's in a memory file system, or you can translate it to key value. That does require a little bit of coding. Okay, scratch that, a lot of coding in order to get the translation between HDFS and key value, but I mean, as we know, the Hadoop's mascot is not a jackrabbit, not the fastest thing on the planet. So any type we can do to speed up Hadoop, it's a good box.
On HDFS, you have petabytes of data, but I don't think you wouldn't have petabytes of memory. So.
You don't?
No.
No. Darn it. See, I'm just trying to convince people to get really, really big machines. First out, last in, first out, by time and date are the same, Rachel, great. It's highly configurable. And then you also, not only just evicting stuff out of cache, you can also choose how stuff gets moved out of heap as well. So you have lots and lots of fine-grained control. And if you're using the Ignite persistent store, you even have further grain control over that. So what have we learned? We have learned Ignite's great. Record, that system record is pluggable. It can be anything JDBC, ODBC, a NoSQL system, or Ignite's own persistence layer. And it provides an in-memory layer, SQL 99, high availability, scalability, and I think I've used all my buzzwords. We good? Excellent. Oh, Spark, sorry. Yeah, Spark. All right, so how are all these things work? We have, first off, the data grid. This is what we mostly been talking about, caching. Some of you guys might be familiar with that. Compute grid is actually where Ignite started from. So Ignite started as a way of distributing code, Java code, around multiple machines. This was such a good idea that people are like, well, what about our data? We're taking time getting the data off the network, off of our big mainframes or whatever at the time, right? Network's only so big. And also, get your data off quick enough. So we put data grid and compute grid together to do co-locate. So those are the two fundamental portions of Apache Ignite. That is what everything else is built on. But we have streaming APIs, messaging APIs, continuous queries, integration with Spark. So you can do OLAP caching, OLTP caching. And my very favorite one, gas. Most of the implementations of Apache Ignite that go over a single use case are people and an application internally. So each group who needs to use in-memory resources uses the API. So this is what's going on. Okay, I've heard of them. American Express, probably heard of them as well. Spearbank, which you probably haven't heard of, but they're really, really big in Russia. Really big bank in Russia. They've actually removed all relational technologies, including Oracle, out of their data center and replaced it all with GridGain. 5 petabytes under management in production. So they've created this started this sort of project. Your pizza and beer was brought to you by a company called GridGain, which does a couple of things: security, LDAP, and Jazz, and authentication, and authorization, everything you need to do, all your wonderfully secure applications. High availability, we'll get back to that. Monitoring and management, we have a nice little see what's going on your grid. This stuff is.
So one question.
Yeah.
Why is it called OLTP caching? Well, I just want to say if the OLTP and OLTP caching, there are some difference.
So what I'm saying is that you can use this for transactional-based caches. So that's what the primary use case is for Apache Ignite, is ACID transactional caching.
So that is only in the memory, that goes to disk.
Correct, yes.
Okay.
Yeah, remember, this is memory first, right? The persistent store, whatever it is a secondary method of, it's there in case something happens versus the primary system of record. So that's the difference in mindset. I'm assuming most of my audience is familiar with it, but that's probably I think most of you guys are from TimesTen though. So. High availability. So when my first job out of college was teaching end user course, and right there, high availability. So that's what we're going to be talking about today. So Apache Ignite in a single data center, it can be configured to be highly available. We talked about primary and backup nodes, but, oh look, I made that flash. That was sweet of me. Data centers fail. For various reasons, stuff's happening out there that makes tornadoes. So it was a little too early for some of these jokes. Toddlers and chickens running around your data center. You might let the chaos monkeys from Netflix out into your data center. This actually happened to me. So I had a data center that I was working with that was outside in Virginia, and it went down, and there was no reason why. Everything looked good. The weather was good, but the entire data center was dark. And it took me a while to sort of figure out that was happening, and it's actually because a truck. That wasn't the actual picture of it happening. I had to Google it, but it's not all just just jokes. They do go down. And this is a heat map of earthquake, tornado, and hurricane hazard zones in the United States. So no place is safe, right? You're not going to be able to find a data center that's safe from all these different natural disasters. But you could use the cloud, and we all know that clouds never go down, but at least it's somebody else's problem at that point. Luckily, GridGain can run either way, and you can make hybrid approach. So you can have multi-data center replication going on to the cloud, to on-premise, any place you want to do, up to 32 different data centers, and I think that's because it's hard-coded to be in Azure. So if anybody asks for more than 32 data centers, all we need to do is change the data type. Should be okay, right? That's just how it works. So, all right. So this is the number of different another different features that you have with multi-data center replication. So basically, the way that replication works is it batches a number of updates on a single data center before sending it to a second data center. That batch can be one. So it can do a single one. Ring Central's our client, and they're doing a data center batching of one. You can filter data. So you can have data that's going from one data center to another, but not all of it. And this is really great in European countries where you've got some data sovereignty issues, where you want to make sure that data from one country is not leaving to the other. This is probably also due to the fact that we're all developed in Russia. Failover, complex topologies, meaning you can be in the cloud, you can be on premise, you can pause and resume, and there's state transfer. And we're going to go through in these a little bit more detail. So let's see how my did I lose it?
No.
Okay. All right. Let's see how this works. Okay. So we have 4 roles within our data center replication. We have a sender cache. So this is, in this case, we've got the cache that's holding the sending, receiving, the data that's to be sent over. We have a sender hub, which is the node within that over in the second data center. It's going to be the one for receiving data. Good job. See, I knew you guys were catching this up. And then the receiving cache, which is the cache that's going to accept it. And the only restriction is that the receiver hubs and the receiver caches are in the same data center topology, and the sender hubs and the sender caches are in the same data center. So you're going to want to make sure that these are not split between data centers, but otherwise you can create as many hubs sending and receiving as for your application. Cache or pass through a filter. But all items that pass the filter are accumulated in batches on the primary data nodes. And when the batch hits the capacity or the time limit that it received the batch is moved from the sender cache. So the hub will act back to the cache will remove it. Say, all right, I'm done with it. If the acknowledgement reports an error or doesn't arrive, the sender cache sends a batch to another hub. If all the sender hubs fail at that point, replication is paused and the batch is discarded. So that's why you would set up more than one sender hub in a topology. All right, next the receiver. So then we have the receiver hub. Oh, sorry. So once the sender hub receives the batches from the sender caches, figure that. Once the batch is saved, it acts back to the sender hub, the receiver hubs. Data center, and you configure all that, and I'll show you all the configuration parameters in a little bit. What is the data?
It's like a physical record, or is the upper layer and the second layer?
The record, I would say.
Is it the disk block or the memory block?
No, it would be the actual record itself. So whatever, so the data, so it's not a...
It's like a key value store, you update one record there, you will duplicate the whole record to the other side?
Correct. That's the point of multi-data center replication, right? Is that you are creating an active-active or an active-passive environment.
So if you update 1 byte in the record, you still duplicate the whole record to the other side, even that site already have it?
So this is a key value store, right? Yeah. So this is, just one key and one value, right? So there wouldn't be an entire record.
Could be big, right? Could be like
True. Yes, it would probably it will update the entire record. This is memory, so yeah, this may cause a bit more memory than out of all the things that I talked about Apache Ignite, I never said that compression was something that it did. So its use of memory is not designed to be small. Its use of memory is designed to be fast. So we're going to err on the side of speed rather than the side of compression.
So how do you know the data on the master node on the sender side is changed and you need to duplicate it to the other side?
So yeah, we're going to talk about that. So basically, it acts back. So we'll get there in a little bit about what it was. Yeah.
So just clarify. So the data in the memory is compressed with some.
It is not compressed.
It's raw data.
It is not. The data that lives in memory is not compressed. No.
But if you use some encoding like PLE, you can compress the data significantly.
True. And there are some discussions around doing it. But for the most part, the reason why we have not implemented compression is because of this is designed for speed. And if you're going to compress data, you have to uncompress it at some point. There is some discussions. You can definitely go and join the Apache Ignite user group, and you can see the discussions that are going on currently about the compression options.
Yeah,
we're learning what it is. We're not telling them how to make it better. So they're telling us what it is.
And we will happily hear things about getting better, just I can't do anything about it. If Dennis was here, Dennis could do something about it, but I just talk about the stuff. So he's the PMC and the product manager. Yeah. He does a lot of talks, but he speaks to do this the presentation today. I don't know if Tom will ever let me do it again.
Yes.
He's like, oh, Russian's so much more controllable. Okay, so once the receiver hub receives the batches from the sender hub, it stores them and it acts the receipt, right? It says, yep, I got it, and then it allows the sender hub to remove the batches from its store. So what we're saying here, right? So the cache person sends it to the sender hub. Sender hub says, I got it, removes it from the cache. Sender hub sends it over to the receiver hub. Receiver hub says, yes, I got it, removes it from the sender hub. So we are using memory efficiently here, right? We're not duplicating in a whole bunch of places. And then once it goes into the receiver cache, same thing. We'll remove it from the receiver hub. So there's conflict resolution, race conditions. We love them, right? Two different, if these are active-active, you've got information coming in over here. We've got, Rachel at GridGain coming in over there, Rachel at GridGain coming in over here. What do? We have conflict resolution for that. And there's different options there. You can use a new one, you can use the old one, you can merge them, and the default is use new, and that's based on a timestamp. That is exactly how replication works in Cassandra, by the way. So you're getting a 2-for-1 education lesson today if you're not familiar with Cassandra Multi-Data Center Replication. Nice. And that was just one of those things that I'm like, wow, that's easy for me to learn, isn't it? Okay, so we receive batch from the sender cache. We save the batch to memory. Save the batch to memory on disk. We acknowledge that we have it, got it. We send that to the receiver hub, receives acknowledgement, receiver hub says yes, and deletes the acknowledgement from the local store. Everything's fine and dandy. And I did forget to mention these can be set up to be active-active or active-passive. So you have both options for replication. All right. So the entry filters are applied at sending, and then there's the conflict resolution as well we talked about, in case there is a race condition or some other type of conflict on the data. All right. This is a conversation that we all have to have. Not rarely do I get a client who says, right, we have 2 data centers. We have one in Japan and one in San Francisco. And we would like to have active-active, and we want ACID level consistency. So typically I say, right, okay, so the speed of light, can't do much about it. So keep that in mind. There is limitations based on how far away your data centers are on whether or not you are going to be able to get the type of SLAs that you're expecting from an in-memory solution. That being said, we do not offer currently any type of ACID level guarantees between data centers because that would be silly. But we're working on it. We're working on that. And you say, and go faster. Doesn't work like that. You write an application, you configure GridGain to work, and then you write your application's APIs to work with GridGain. You're always welcome to look this stuff up. This is defining the data center ID. This is the sender configuration. This is the receiver configuration. This is how you set up replication filtering. And this is how you tell the sender to use the filter. And you use the conflict resolution. So each of the steps that we went through, I can send you this presentation that's also in the documentation. When should you do this? Now, because we need to have a when in there, right? Do it now. This actually comes from if you're designing an application and you're just using a distributed system and you want availability guarantees, it's good to build it in from the get-go. There's so many times where actually just today, the government has this RFP out and they want you to do the fastest thing possible and they don't have any availability tests built in. And I go, like, are mutually exclusive? And they went, oh yeah, we should probably, like, what type of tests do you recommend? I'm like, a kill -9. It really just, any type of tests out there. So it's amazing how many people do not design for availability. So what did I tell you? I told you all about Ignite and GridGain, maybe a little bit about Cassandra. It's essential for your modern data-intensive application. Yeah. Oops. Like that image of a unicorn cloud has gotten me so far on presentations. How does it work? We went through that ad nauseam. Right. Good luck with that. Thank you very much for that. Appreciate it. There's a lot of things to remember on that particular slide. All right, go for it.
Since you're done.
They should have Brian present.
Yeah.
Rachel, could you get Tiffany?
Do you want me to help you? Because I think it's that. Sorry.
It's complicated.
It's complicated. Right. So.
One click wonder.
Yeah, just click
All right.
anywhere.
So we go to Windows. Yeah, and then you have to, and then we there we go.
One click.
And then it's going to connect to the base unit, and then you're going to push the buttons.
Okay.
Because after all of that, then you push the button. You see my cables, they work great.
Alrighty, thank you Rachel for that. I'm not going to be quite as animated as Rachel. So I've got a bunch of stuff, so I'm just going to go through it. I'm sure you're going to ask questions, so we'll just deal with the questions as we go. I've got demos, I don't think we're going to have time for those. So I'm going to be talking about a new product, Oracle TimesTen Velocity Scale, explaining what that is. I work for Oracle, I'm a product manager, and basically this product is all about going fast, being scalable, and being highly available. So if you only need to remember three things, it's fast, it's scalable, it's highly available.
Yeah, I've heard that before. You said it myself.
So first of all, who's heard of TimesTen? So for the people who don't work for TimesTen, we've got thousands of customers. It's embedded in a lot of things. Basically, if you use a cell phone, you're using TimesTen. If you're doing stock exchange changes, basically using TimesTen. It's all over the place, embedded in things. So recently, Forrester Wave put out one of their Magic Quadrant things. It's looking at in-memory technologies. The trick is to be at the top right of the chart, and that's where we are with Oracle. So the combination of TimesTen and Oracle in-memory, according to Forrester Wave, is the best at execution and vision. So there's a bunch of other players out there. The point being, we're at the top.
Question. So you are saying Oracle is better than HANA?
According to Forrester Wave, yes. So HANA used to be at the top. The marketing hype sort of dropped away. They've looked at features and functions and what's implemented. I can throw things at that. So TimesTen was the first commercial in-memory database. That guy over there, he was one of the originals. So it's been around since '98. So you may not have heard of it, but it's been around for a very long time. So it was acquired by Oracle. They've made it a lot more compatible with the Oracle database. So TimesTen is a SQL relational database. Acquired by Oracle, they've made it more compatible. Similar data types, similar features. So when I say it's a relational database, it's just a relational database. It's not NoSQL this or NoSQL that or key value, whatever. It only does SQL, but it does SQL really, really fast. Everything's in memory. If you've got a lot of data, it's got to all fit in memory. So about 8 years ago, we used to do multi-terabytes. That works, but it's expensive. So what I'm talking about today is how, instead of scaling up in really big boxes, how you can scale out horizontally. You can go faster and be more available. So it's an in-memory database. It uses ACID transactions, standard SQL. But what happens if you pull the plug? What happens if you reboot the machine? Doesn't matter, we still persist the data to disk. Is it a spinning disk? Is it an NVMe disk? That's just how much money you've got and how fast you want it to go. The point is we persist it to disk. So it goes fast in memory. If you reboot, someone pulls the plug, it can recover from disk to a transactionally consistent point, just like an Oracle database would. It goes really fast. We've got high availability stuff. I'm going to go into that. So when I say fast as a SQL database, we measure things in microseconds rather than milliseconds. So what we're looking at here is SQL selects based on primary keys in under 2 microseconds. Updates about 5 microseconds. So literally, if we're not waiting on the disk, if we're not waiting on the network, we're just worried about how fast the CPU goes. So literally, the faster the gigahertz, the bigger the L3 cache of the CPU is how fast TimesTen will go. So if you've got a gaming machine going at 5 gigahertz, that can be really fast. We're just talking 2.2 gigahertz. This is a 4-year-old machine. So pretty modest hardware. You're doing SQL operations in a matter of microseconds. So it's all about going really, really fast. So obviously mileage will vary. If you're doing a select on a primary key to return 1 row, that's pretty simple. If you're joining 20 tables, it's going to take more work, it's going to take longer. But the simple operations can be incredibly fast. As a result, you can scale up. So this is just using the existing product, one machine. Because individual operations are really fast, you can scale up. So we're doing a mixture, 80% reads, 10% writes, updates, deletes. So it's a mixed workload there. We're doing over 5 million transactions per second on a Linux box of 1 new machine. So a little cheap machine can do over 5 million transactions per second read-write. Run on a big Spark box, goes even faster. So we can scale up and we can scale out. So that's just examples of how we can scale up. So TimesTen, this is what confuses most people, is a relational database. You can run it in 2 modes. You can either run it as a system of record where there is no other database, or you can use it as a read-write cache for your Oracle database. So about half of our customers use it as a system of record. There's no Oracle, there's no anything else. It's just TimesTen on its own. The other half use it as a read-write cache for the Oracle databases. Okay, so lots of details there. That's not the focus of the talk. The point is it can do it. When you do use it as a read-write cache, it can go really fast. So if you have an Oracle database which is disk-based, if all the data blocks of interest are loaded into memory in the SGA, so the Oracle database is not hitting disk, we still expect to be, on average, 10 times faster. So in this particular workload, this is latency, the blue bars, 1,000. That means a millisecond. So the Oracle operations are taking about a millisecond or less. These really small numbers over here, that's the latency for TimesTen. So we've got exactly the same data model, exactly the same data, exactly the same workload, exactly the same JDBC program. You're either going directly against Oracle or going to TimesTen as a read-write cache to Oracle. So that's why our customers that use TimesTen as a read-write cache for Oracle, be it Oracle or RAC or Exadata, do it to get lower latency. So what I am going to be talking today is about the right-hand side. Our existing products is an in-memory database. Virtually everyone uses it in highly available configuration. Mostly active standby, you have a lot of different subscribers. The point is, it's extremely low latency, you can have high availability. The problem is, if it's active standby and you've got a read-write workload, the scalability is limited to the write rate of the active database. So you can add lots and lots of readers to scale your reading, but you're going to be limited by your active of how much writes you can handle. So that's the existing product on the left. On the right, we thought, hey, this in-memory database is really fast. Why don't we have lots of them? Why don't we scale out horizontally? So what we did is we took lots of them, we scaled it out, we changed the SQL so it works transparently across this distributed database. You just think it's one database, it's actually spread over many machines. You're doing SQL operations. What we want is for your application and your schema not to have to change. We make that transparent for you so you don't have to change your application. So everything's active-active, so your writes scale as you add more nodes. Your reads scale as you add more nodes. So to keep it simple, more is better.
Sorry.
Yep.
On the previous speaker, someone was asking about how you do distributed joins.
Yep.
How would we handle
Yeah, that is a great question, and in about 4 slides, I'm going to go into that in detail. So if you can just hold on to that thought. So just, we've heard from Rachel how GridGain and Apache Ignite do it. This is different technology solving similar problems. Some of our approaches are the same, some are different. So just because Rachel said it did it one way doesn't necessarily mean it's how we do it. I'm saying how we did it. So logically, everything's interconnected. The point is, you see a single database image. You think it's one database. You see a schema. So whether you want to think that as a an Oracle database or a SQL Server database or a MySQL, you think of it as one. It's spread over many for availability and scalability. So here's the secret sauce. If you've got, so this is technically a scale-out shared nothing database. If you're naive about it, if you've got, because it's a relational database, you've got tables with primary keys and foreign keys and your joins. If you're naive about it, you need to send rows across the network. It'll work, but it's going to be slow. So the way to optimize this is to minimize the amount of stuff you send over the network. Sounds pretty obvious, but it's actually fairly hard to do, given that you can be doing arbitrary SQL. We can't control what your data model is. It's whatever you want it to be. We can't control your SQL, but we can help you declaratively set things up to minimize those message hops. The less hops, the faster you go. When it all runs in memory, you've seen with TimesTen on the single machine how fast it can go. So it's all about optimizing it to minimize those network messages so you can go faster. So if you've got a data model, you're arbitrarily, customers, orders, catalog, that's just arbitrary tables. The point being, if you can co-locate data, so when you're doing joins, so you do joins in memory on the same machine, that can be blazingly fast. Okay, so if you've got something like customers and you want to join with the orders table, if you co-locate the detailed rows from the orders table with the rows for the customer, it can go faster. So we literally do that on a primary key, foreign key basis. Likewise, if you've got some tables that you want to join with a lot, we can do a Spacetime Optimization. If we literally have a copy of that table everywhere, the joins will be very fast. So the benefit is it's really fast. The cost is it's going to take more memory because you copied it everywhere. So these are all trade-offs. You don't need to do any of this. It's transparent. This is to make it go faster. So the point is we do this at the table level so that the SQL, the selects, inserts, updates, deletes, don't see the stuff.
Are these like hints?
Yeah, I'm about to show you.
Okay.
So here's an example. Create table. That's supposed to be read there. We try and use the Oracle syntax. Create table. So at the end, that's the end of your table. This distribute by is the new bit. If you don't specify anything by default, it's going to distribute by hash based on the primary key. You can do it on arbitrary columns. It doesn't even need to be the primary key. The point is, that's the default. When we're distributing by reference, you choose one of your foreign keys to co-locate to join the rows against. Likewise with the duplicate. So we're just sprinkling a little bit of syntax to your existing tables. So because you're doing it at the DDL level, the table level, the applications don't know about this. It just works. It's transparent. Okay, I'm not going to go into the details here too much. The point is, we're focused on OLTP. By the way, we also do analytics. We do things like cubes and roll-ups and width. So we do OLTP really fast. We can also do the basic analytics operations very fast as well. So logically, we've got a fully connected mesh. In practice, what we do is we have copies of the data. So imagine you've got a really big database. Let's logically split it into 4. So you've got 4 different quarters, A through D. If you split your database up into 4, and one of those machines goes down, that's a problem because you've lost a quarter of your data. But if we have multiple copies of that data, we can mitigate that risk. So we split the data up over as many machines as you want, and then we have copies to keep it highly available. So the beauty of this is it's active-active. There's no active standby, there's no master-slave. Because it's active-active, you can do reads and writes from anywhere, which means programmatically it's really simple and it scales. So basically, the more we split the database into more machines, the more scalability, the more effective availability that we get. So we can initiate our transactions, run our queries from any machine. Okay, what happens if something goes, what happens if there's a failure? If I'm having a really bad day, I could lose half of those machines and everything's still going to work. Because I've still got a copy of A, still got a copy of B, C, and D. So at least one copy of the data is everywhere. So that means my SQLs, my select, my queries, my inserts, my updates, deletes, they're still going to work, even though I've physically lost half of my machines. If I'm having a really bad day, and in this case, lost both of those, what happens next is actually your choice. This is application specific. If for your application it doesn't matter, and it's perfectly okay to keep processing with what you've got, we can handle that. You tell us that behavior, we'll do it. If that's not okay, we can say, whoa, let's give an error and let's stop. So the point is, it's application specific, that behavior, you tell us, we can even do that on the fly at runtime via a hint. So did that answer your question? Okay. So please ask questions. So maybe I'm explaining it too well. Who knows? So also, we've got a scale-out database. You can grow and shrink your grid, add or remove machines as you need. Is it month end? Maybe we need more machines. Is it year end? Grow and shrink as needed. So we've got an example here. We'll split the database into 4. Can add some more machines, and then we can move the data. Take a little demo later if we have times to see how we do that in practice. That's the theory.
What is the typical node?
Sorry?
What is the typical node?
I can't
What
hear
does
you.
a typical node look like?
What is a typical you mean, so this all runs on Linux, 64-bit Linux, so it's a Linux machine. Is it a little itty-bitty machine or a huge machine? That is your choice. So basically, you pick your favorite Linux distribution, pick your favorite hardware. Is it an HP? Is it a Levino? Is it a Sunbox? We don't care. It's a Linux machine, and how big and powerful or small and cheap it is your choice.
So it doesn't have to be Oracle Linux.
Does not have to be Oracle Linux. I've got some slides. Basically, you pick your favorite Linux distribution. So any other questions before I go into the next bit?
Java or C?
The runtime is C, but that's hidden from you. You as a programmer use JDBC or C#, whatever your favorite language is. Our runtime is C. Okay, so I said it's really fast. How do you know it's fast? So I've just got some examples of some OLTP benchmarks here, and we'll look at some analytics as well. The first one, YCSB, have you guys heard of that? So incredibly simple, gets and puts. I'm just looking at the 95 read, 5% write there. TPTPM is a telco benchmark. It's a SQL benchmark. We're looking at very simple workload, 80% reads, 20% writes. Sysbench, so that's been around forever. It measures your CPU, it measures your file I/O, and it also measures SQL operations with MySQL. Been around forever. I'm doing it because Google and AWS have started using it as a standard for workloads. So we're just reproducing that workload. So that's more complicated, 14 different SQL operations, so it's more the transactions are more complicated. The last one is an order management. So if you, things like the e-business suite, CBOL, incredibly complicated. You've got thousands of tables, you're doing orders, lines, fulfillment, unbelievably complicated. So we're looking at various different workloads, from trivial to more complicated. It's easy for a database to be good at one benchmark. A really good database is good at all benchmarks. So for this first one, last year Google put out a benchmark saying Google Cloud SQL is better than Amazon Aurora. Whee! So they'd spent a lot of time making their product faster than Amazon Aurora, and they used Suspense to do it. So what they did is it was a really hard configuration. Rachel talked about replication between data centers. This workload is doing replication between data centers. It's doing synchronous replication with ACID transactions. So it's all about high availability. Because you're doing synchronous replication, the network round trip is a dominating factor. So the numbers you get aren't particularly high. But you're doing replications between, so they were doing it in the Amazon cloud and the Google cloud. So they're doing it between availability zones or availability domains. So literally between data centers. So you're doing these mixed transactions between data centers. So Google said we're faster and came up with some numbers. Amazon very quickly said, actually you didn't configure Aurora very well. They reran it. Turned out Aurora was slightly faster than Google. So what we had was a well-defined benchmark and optimal numbers for Google and for Amazon Aurora. So we just duplicated that. We ran it on velocity scale. This is throughput. Big is a better. Now the interesting thing is MySQL, Google Cloud SQL, and Amazon Aurora, they all use an active standby configuration. That means they can scale reads because they can keep adding machines, but they cannot scale writes. They can have a bigger machine, but there's a limit to how big the shape of that machine can be. Once you've hit that limit, once you've got the fastest SSD disks you've got, you can't go any faster. So that's throughput. Latency, small is better. We have the best throughput, lowest latency. The interesting thing is, so we were looking at this stuff over here, between two machines, between two data centers. As you add more machines on velocity scale, it scales up because we're active-active. We can scale the writes. MySQL, Google Cloud SQL, Amazon Aurora cannot scale their writes. So we can just, it's linear, we just keep adding machines. So that's the first benchmark. It was 14 operations in a transaction, select, insert, update, delete, moderately complex SQL between two data centers, pretty slow versus scalability. Next workload. This is the most complicated one. Legally, I can't say who the customer was, but they sell things online and they have department stores where you can go to buy things. You've probably heard of them, you've probably shopped with them, possibly every month, possibly every week. The point being, they do so well in business, they wanted to ship things quicker. Like, they've got a website where you click, I want it in 4 days, or I want it in 2 days, or I want it in 1 day. And the shorter the span, the more you pay for that shipping. So their problem is, what say something was out of stock, and the customers said, I want it in 2 days, but we didn't have it in stock. But now suddenly it's in stock and I've run out of time. They need to optimize to ship it to you on time and minimize the cost, because they need to work with vendors who ship things, who have different costs. So they're optimizing it to minimize cost. You just want it to turn up on time. The point is, they're selling so much stuff, they couldn't do it on time. They had an existing Oracle solution. They wanted to go faster. They picked a NoSQL solution for that, and it went twice as fast. They were happy, it went twice as fast. instead of joining these thousands of tables, they denormalized it, and they had these big fat tables. Went really fast. So every day they loaded the data from Oracle into this in-memory data grid, it went fast, and at night they wrote it back again. So everything was good. They had a commercial issue where they couldn't keep using that technology. So they had to look at how can we go really fast and be consistent. They had problems with consistency. Relational databases, ACID transactions, pretty good at consistency. NoSQL databases have issues with consistency. So they wanted to be faster and have consistency. So they did lots of research and they came up with 3 different products. MemSQL, VaultDB, and Oracle Velocity Scale was these technologies they looked at. So we had their system with thousands of tables. So we had the existing Oracle schema, the existing Oracle SQL, and the existing NoSQL, and they say, do the equivalent. So this was complicated. It took us all months to do it. The point being, we did the 2 different proof of concepts. So Velocity Scale was 10 times faster than MemSQL. VaultDB turned out they couldn't run the SQL. This SQL was complicated. The simplest SQL was joining 5 tables. Most of them were joining up to 20 tables. So Velocity Scale was 10 times faster than their NoSQL solution. So the NoSQL solution got rid of the joins and these big wide tables, key value. Even with joins, we were 10 times faster than NoSQL. We just used the existing Oracle schema in SQL because we didn't want to figure out how to do it. We were compatible, we just did it that way. So we did the OLTP and batch stuff really fast. So I can't tell you who the customer was and exactly what they were doing, but believe me, it was really complicated. Scaling. So before I talked about the TP-TPM benchmark, it's a telco thing. It's really simple SQL for what we're doing. We're doing selects and we're doing updates. We're doing 20% updates and 80% selects. What we did is we added more machines and looked at the throughput. And as desired, we got linear scalability. So along the bottom here is the number of machines we'll be using. We went up to 64 machines, that's how many they gave us. So what we found is using this workload, 80% read, 20% writes, we got linear scalability. We were doing 144 million transactions per second. Okay? We thought, where's the bottleneck? It turned out the updates were the bottleneck because we're doing ACID transactions. You know, we've got undo, we've got redo, we need to deal with those things. We found out if we turned off the updates, we scaled even better, all the way up to 1.2 billion selects per second. So the bigger the machine you can use, the faster it's going to go. So it's how big the machine is and how many machines. So we used 1 new machines, 2 sockets, going at 2.3 gigahertz. So not very fancy machines. Once again, about 4 years old. 1.2 billion SQL selects per second. Pretty fast linear scalability. So just doing a comparison here, it's really hard to do apples to apples comparison unless you buy all the products and benchmark them yourself. You've got to look at existing benchmarks. Existing benchmarks might be years old or using older versions of the product. So what I've done is I looked at basically the best configurations they've ever got. So this is once again using the 95% read. So Cassandra scales really well. You know, Netflix did a benchmark, they had thousands of machines, scaled really well. They did 1 million transactions, but it took thousands of machines. So it's pretty fast. Am I running out of time?
No, I'm just going to tell you that Cassandra can't read.
Sorry?
Cassandra doesn't do well in YCBS because it doesn't read well.
Absolutely.
I would never use Cassandra for a read-heavy application.
So I totally agree with you, Rachel. The best so I'm missing a column here. Cassandra didn't do very well on this benchmark. This is a NoSQL benchmark. Cassandra's NoSQL, they didn't do very well. Mongo did better. Couchbase did a bit better again. Redis, really, really simple, but it does what it does really, really well. A lot faster. VoltDB was better. Aerospike, they're pretty good. We got the best number, but that's only half the story. That was doing gets and puts. 95% reads, 5% writes. You look at the numbers, what the throughput is. The interesting thing is, how many machines did you need to get to that point? Cassandra needed 32 to go really slow. We did 2.8 million with one machine. So the faster your box, the better. If you've got a really fast box and a really fast database, you just add more machines. Okay?
What is the memory system?
Sorry?
The memory system.
Memory system.
I still.
Just the
what's the memory system?
Or is
What?
there any 3D cross point or
No, no. This was technically. So for velocity scale, we used Sun X52 machines. So they are not fancy machines. They are 1U. They've got 2 sockets. I had the numbers up before. They've got 2.3 gigahertz Xeon CPUs, and they just got DRAM. Nothing fancy. We did have NVMe disks to write to, but once again, that was even the latest and greatest stuff. So we were using Xeon Broadwells. Xeon Skylakes are the latest and greatest. So we were using literally 4-year-old technology Broadwells, and we were getting 2.8 million YCSBB throughput per second. So it's not. So the point is, you can get a lot with pretty modest hardware because it's very efficient. So that was just one machine. This is a very old benchmark, velocity scale. We're about 300,000 there. This we did a couple of weeks ago. 2.8 million is way off the chart. So we need to redo the benchmark. We just need some more machines to do it. So the point being, a year ago we were scaling. Question?
Yeah, so does the number of cores in each machine matter?
Yes, it does. Absolutely. If you're looking at throughput and concurrency, the more cores you've got, the more stuff you can do in parallel.
So how much is the significant factor? Is it near linear or is it close to linear?
So that looks pretty much linear to me. So with TimesTen, if you're doing reads, it's pretty much linear. Does that answer your question?
Yeah, so then do you have any special processing for the NUMA out there if you have multiple cores?
Good question. So for the NUMA-aware things, if you've got a huge SMP box with 16 sockets or something, you need to worry about that more. We had lots of little machines. They had 2 sockets and 72 cores. So the NUMA issues weren't so much of a factor. Any other questions? That was OLTP. Velocity scale is focused on OLTP. It also does analytics. We're not focused on that, but it does it pretty well. We're looking at latency. Smaller is better. So this is the Oracle analytic workload. So what that means is they took the TPCH data model and data and they changed the queries to make them harder. So these are really hard queries. When you've only got one velocity scale machine, it was taking over 1600 seconds. So this really fast database was taking a long time. As we added more nodes, it was basically halving each time, so we got it down to a couple of seconds. So as you add more nodes, analytics things with a lot of group by type stuff goes faster. So this is not published, but this is TPCH. According to me, velocity scale is the 3rd fastest ever. So we're talking faster than SQL Server, Sybase, and UDB. The guys that beat us were very specific columnar dedicated machines. So it's not the fastest, but it's pretty fast. This one, so if you've heard of MapReduce, Hive, Pig, there's lots of different technologies. they have this thing called the Big Data Benchmark. So a couple of years ago, Amazon Redshift said, hey, we can do the equivalent of that benchmark using SQL. They defined a table, they defined some SQLs, and they ran it. So you probably can't read it. The point is they were comparing against Impala, Shark, a bunch of different technologies, Hive, and it turned out that Redshift was faster than all those guys doing the same benchmark. So an analytic, massively parallel database, relational database, was faster than all those MapReduce technologies. So Amazon Redshift was faster than all of those. I just did the same thing, used the same table that Redshift did the same SQL, bunch faster. So by implication, we're also faster than all those MapReduce things.
Those are older versions of Hive.
Correct. I mean, I wasn't running the Hive stuff. They published a benchmark. I'm just saying what they did. They will get better, they will get faster. That's a data point. You're right. I mean, it's every new version they tend to get better. So, we've talked a lot about velocity scale. It's SQL, it's relational, it's in memory, it's fast, it's scale out, it's persistent, it's highly available, it does OLTP really well, it does analytics fairly well. What's the gotcha? Currently, it's not released yet. We've just finished beta. We did 4 rounds of beta. So we had customers in Europe, in Asia, in the US. This company you've probably never heard of. They're a South Korean company. The interesting thing was they did the beta, we did some training. They then, within an hour, got their existing app and got it running on velocity scale without changing their schema or their code, it just worked. So they were very happy. They didn't have to rewrite their app to work with this new scale-out product. They didn't have to change their database, they didn't need to change their application. This South Korean company you might have heard of, Samsung, they were pretty happy with velocity scale. Samsung does a lot of things. This is their telecommunication part. China Mobile is one of our biggest customers. So, you know, China Mobile, China Telecom, China Railways, all run TimesTen. They're huge. They want to go to this solution. They currently use manually sharded databases with TimesTen. It works, but it's a lot of maintenance for them. By going to velocity scale, where they don't need to manually shard anything, we do it for them, it's all transparent to the application, they get the benefits with less maintenance. That's why they want to use it. So the point being, we can scale better than NoSQL while still using SQL. We can go faster than NoSQL databases even though we're doing joins. We don't need to denormalize. Keep your schema as it is. You don't need to manually shard it. We do all that automatically for you. And you don't need to rewrite your apps. That's the value proposition that we're looking at for velocity scale. So just quickly, the lady had the question before, where does it run? So Red Hat, CentOS, SUSE, Ubuntu, Koros. I haven't found a distribution where it doesn't work. Technically, as long as you've got glibc 2.12 or later, it's going to work. So Red Hat 6.4 has got that version of glibc. Red Hat 6.4 is ancient. So, like, you know, Koros isn't really a distribution, it's just the latest kernel and it'll download the stuff on the fly. Those other ones are distribution. So basically if you've got a Linux distribution within the last about 5 years, it's going to work. Does that answer your question? So that's Linux. We run on 64-bit Linux. It'll run on TCP or IP on InfiniBand. You need a file system. You need enough memory for the system to run on. So the actual requirements are pretty minimal. Pick your favorite VM or hypervisor. Works on Docker, works on Rocket, works on OpenStack. I tested this, tested this on Azure, tested that on AWS, tested that on Google. VirtualBox is an Oracle thing, that's an Oracle thing, VMware thing. So the point is, I haven't found a Linux 64-bit system that it doesn't run on. So the point is, it's software, run it on your favorite hardware, run on your favorite Linux distribution.
How does it compare price-wise, cost-wise?
Really good question. Flat out, the answer is I don't know. This guy called Larry Ellison at Oracle is going to define the price. He hasn't done that yet. As soon as we know, I'll tell you because I want to know.
Do you think there would be like a community edition?
No.
You can always download it, right? You can always download it.
Yeah, with the TimesTen, you can download the existing one. You'll be able to download that. You can use it for free. The minute you need support to fix a bug, they're going to say, what's your customer service number?
Oh, you can download it?
You can,
Yeah, so if you go to Oracle Technology Network, you can download it for free today. So that's the existing product. This one we haven't released yet. As soon as it's released, you'll be able to download it.
Larry else is famous for saying if people are going to steal software, I want them to steal mine. And so every Oracle product is available for download often.
Correct. I think I've gone over time. Bunch of screenshots, so I'll just jump through those. Cut to the chase. We've got a scale out, shared nothing relational database. You don't know or care where the data is. You just connect and do your SQL. Is it on this machine or that machine or some other machine? You don't know, you don't care. It just works transparently. We've got high availability. We showed that. You've got multiple copies. You can dynamically add and remove nodes. We've made it really easy to deploy and manage it. It's focused on OLTP workloads, or to work on-prem or in your favorite cloud. So, great questions. Do we have more questions?
How does it compare with Exadata?
Okay, that's a very political question. We've done some bench.
But
So the cost and
the answer, sorry, my name is Sam Berry, I'm the architect for the product. Exadata is a wonderful solution for scalability. If you need the fastest possible response time, that Exadata box is always a network hop away from your apps. You don't run your app in the Exadata box. You can run your apps on the same nodes that are running this. And so if you need low latency, this is a better solution.
Great answer, Sam. So price, we can't compare because we don't yet know the price of this product. We are a software solution, so you can run it on your favorite hardware. Exadata is an excellent solution. If you want to go as fast as possible, if you want to be as simple as possible, we think this is a better solution.
So you haven't talked about the central management.
No, we've run out of time. Any other questions?
so does it support the notion of plugging in databases?
Does it support the notion of pluggable databases?
No. No, that's an Oracle concept. No, we don't do that. Any other questions? Okay, thank you. So I think Tom's about to do some giveaways.
Yes.